Welcome to video number 2 in our Sequences and Series unit. This is information now about arithmetic sequences. You'll see here an arithmetic sequence, 1, 3, 5, 7, and 9. Being astute math students, you will notice that to get from one term to the other, we simply add 2. Any type of arithmetic sequence always has the same number added between each term. So when we see this addition pattern here, that is the mark of an arithmetic sequence. We call this number that is added D. D equals 2. Now, what about subtraction? Well, that's the same thing as adding a negative number. So if I went 9, 7, 5, 3, 1, for example, D would be negative 2. Now, recall the definition of a function. A function is a sequence, or a definition of a sequence, I'm sorry. A sequence is a function whose domain is the set of positive integers and whose range is the terms in the sequence. So let's set up a little chart here. We'll call our term number n and our term a sub n. And we know that a sub 1 is 1, a sub 2 is 3, a sub 3 is 5, a sub 4 is 7, and a sub 5 is 9. Notice that, once again, that we go up 2 every time. Now you should recall from a previous unit that when something goes up in the same amount in the x direction and in the y direction, in other words, we have a constant addition pattern, that this is a linear pattern. Indeed, if we were to graph this sequence, we would clearly see this linear pattern. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5. This is n. This is a sub n. So we have 1, 1. We have 2, 3. We have 3, 5. We have 4, 7. And we have 5, 9. Okay, so we have a linear pattern. Reminder once again, don't connect the dots. This is known as a discrete function. In other words, it has certain countable values, and you can't just have an infinite number of values in between because the term number has to be an integer. Now let's move on and talk about now how could we write a rule for this sequence. There are two different ways to write a rule for a sequence. We looked at one of them in the previous example in the introduction. We actually wrote what's called an explicit rule, but we're going to start with something called a recursive rule. A recursive rule is usually the easiest to determine because it's more intuitive. When we look and see, how do we find the next few terms? Well, we know we just keep adding 2. So basically in our minds we're thinking we start with 1 and keep adding 2. So when we do that, and do that in a mathematical and symbolic way, we say, to start with 1, we say a sub 1 is equal to 1. So that means start with 1. And then for n greater than or equal to 2, we say a sub n is equal to 1, scratch that. We need to add 2 to the previous term. So in other words, to get from 3 to 5, I add 2 to 3 to get 5. To get to the next term, I add 2 to 5 to get 7. I add 2 to 7 to get 9. I add 2 to 9 to get 11, and so forth. So I need to have a symbol that represents adding 2 to the previous term. Well, if the term I'm looking for is a sub n, then the previous term must be a sub n minus 1. So I say a sub n equals a sub n minus 1 plus 2. So the entire rule is all of these things. I have to know where do I start. Then I have to say for the remainder of the terms, for n greater than or equal to 2, then this is what I do. A sub n equals a sub n minus 1 plus 2. So this is saying a sub 1 is 1, a sub 2 is equal to a sub 1 plus 2, which is 1 plus 2, or 3. A sub 3 is equal to a sub 2 plus 2. A sub 2 is 3. I just found it. So I take what I just found here and plug it in and say 3 plus 2 equals 5, and so forth. Now, this rule is pretty easy to generate. It's pretty obvious, not hard. Probably the most difficult thing about the recursive rule is that you have to remember the format. It actually has 3 parts to it. It has a first term. You have to say which other terms this works for, and then you have to have the rule. So there are 3 parts. You can't leave any of the parts out. If I just said a sub n is a sub n minus 1 plus 2, you wouldn't know where to start, and so that rule would be pretty useless. The disadvantage, however, to the recursive rule is, what if I want to find the 578th term of the sequence for some reason? I don't really want to have to find the 577 terms before it in order to get to the 578th. That would be a very tedious process, although a computer does this very quickly. That is why recursion is a natural thing for a computer to do, or a calculator, because you can just set the starting point, give it a rule, and set it to run, and it'll quickly do it. But for our human brains, a little more direct equation would be nice to have. And because this is a linear function, there's a couple ways to do this. One of them is using a linear function. We could say f of n is equal to starting point. Well, our starting point we don't really know, because we don't know when n is 0, although it's easy to figure out. But we do know that we go up 2 every time in the y direction when we go 1 in the x direction. Well, if we're going up 2 in the y direction for every 1 in the x direction, that means just we have a slope of 2. So this value d is the slope. That is the slope of this line. So we can say f of n is 2n plus, well, I want to make sure that when n is 1, that I get 1, because that's my first term in this sequence. So when n is 1, I want to get 1. So if I plug in, I know that when n equals 1, f sub n has to equal 1. So if I put 1 in for n, then my y-intercept would have to be -1. So in other words, f of n is equal to 2n minus 1. And that makes sense, because if we went 2 backwards, say n was 0, we would go 2 backwards and we would see a sub n as -1. It should also work for any term in the sequence. So if I plug in 5, I should get 9, for example. So that's one way to write the function rule. Another way to write the function rule, and this is known as the explicit rule, and I'll write that down in just a minute. Another way to look at it is to look at the pattern. We see that a sub 1 is equal to 1, a sub 2 is equal to 1 plus 2, a sub 3 is equal to 1 plus 2 plus another 2, a sub 4 is equal to 1 plus 2 plus 2 plus 2 again, 7, 5, 3, 1. So notice the relationship between the subscript here, the term number, and how many 2's I add. So if I'm on the second term, I'm only adding 2 one time. If I'm adding on the third term, I'm adding 2 two times. If I get to the fourth term, I add 3 three times. The first term, I don't need to add 2, so I add 2 0 times. So when I think about this, how many times do I add 2? So I can, well, let me simplify this first. So a sub 1 is 1 plus 0 times 2. A sub 2 is equal to 1 plus 1 times 2. A sub 3 is equal to 1 plus 2 times 2. A sub 4 is equal to 1 plus 3 times 2. So in general, we can say a sub n is equal to 1 plus n minus 1 times 2. So if I wanted to find the 578th term, I would just have to add 2 577 times. So a sub 578 is equal to 1 plus 577 times 2. This is n. This is n minus 1. And that turns out to be, for your information, 1,155. So another way to write the explicit rule is to say in general, and I'm going to need to move my example problem here just a second. Let me kind of shift this down. Oh, never mind. I'll fit it in here. A sub n is equal to a sub 1, the first term, plus n minus 1 times d. So here's our a sub 1 is the 1, n minus 1 is 577, d is 2. So there are two different ways to write the explicit rule. One is more like a linear function, where n is, where we need to actually designate that n is greater than or equal to 1, and it's an integer. Or this function rule here for integer n greater than or equal to 1. So recognize when I'm saying n, I'm not saying that I'm starting with the number 1. I happen to start with the number 1 in the sequence. I'm just saying that I'm starting with my term number as number 1. So there's a couple ways to write what are called, this is called the explicit rule, because it allows us to just explicitly plug in a value for n and find any value for a sub n that we want. Now I've got a problem for you to try. What I'd like you to do is to, 1, find d. 2, write a recursive rule. 3, write an explicit rule. And 4, find the 100, and let's see, which one did I want to find? The 200th term. The 200th term in the sequence. So what I'd like you to do now is to pause the video and to try the problem, and then turn it back on and see if you are correct. Finding d for this one is tricky. It's not obvious at first glance that it is actually an arithmetic sequence, because in arithmetic sequence we have to be able to see that we add the same thing every time. Seeing that we have fractions here, an easy way to figure out if there is a common difference, d, is to put them all in with the same common denominator. Alternately, if the decimal is exact, and I'll give you an example when that is not true in just a minute, you could also put it into decimal form. So a couple ways to rewrite this is, and I'm just going to do it in fraction form, is negative 19 tenths. Well, negative 3/5 is the same as negative 6 tenths. Then I have 7 tenths, and then 2 is the same as 20 tenths. Now if we look then at the numerators, to get from negative 19 to negative 6 we add 13. To get from negative 6 to 7 we add 13. To get from 7 to 20 we add 13. So actually in this case d is equal to 13 tenths or 1.3. Now if I had said d is equal to 1/9, for example, that would, you could get a decimal approximation for 1.9, 0.111111 repeating, but you would not want to use the decimal form for d. You always want to use an exact form for d. Always use an exact value for d. So the only fractions that have an exact value are fractions whose denominators only have factors of 2 or 5. 10 has a factor of 2 and a factor of 5, so it makes a terminating decimal. 8, for example, has factors of 2, so it would be a terminating decimal. But however, 12 factors to 2 times 2 times 3, it would not be a terminating decimal. It would be a repeating decimal. So if you want to have a terminating decimal, only fractions that have a denominator of 2 or 5 will work. That's just a little tidbit of information for you there. So that's D. So there's number 1. Number 2, write a recursive rule. Well, we have to start out with a sub 1 is equal to negative 19 tenths, and a sub, and then 4 n greater than or equal to 2, or you could say for n greater than 1, either one, a sub n is equal to a sub n minus 1 plus 13 tenths. Now, if you had chosen to do this in decimal form, you could have said a sub 1 equals negative 1.9. For n greater than 1, I'll use that as an alternative. It means the same thing. A sub n is equal to a sub n minus 1 plus 1.3. So both of these are okay. I think I probably have a slight preference for n greater than or equal to 2 because it just reminds me that I can't use numbers in between 1 and 2. Okay, number 3, write an explicit rule. Well, the easy formulaic way to do it is just to say a sub n is equal to a sub 1, negative 19 tenths, plus n minus 1 times d, 13 tenths. Okay, so that would one way to do it. We could also simplify this a bit and put it into a function rule. We could say, okay, well, I know that my slope is 13 tenths, so I could say a sub n is equal to 13 tenths n, and then how do I find my y-intercept? Well, I could plug in a point. Probably I want to have my first term be negative 19 tenths when n is 1. So how do I get to negative 19 from 13? I would have to subtract. Let me get my little calculator out here. So I should have prepared this ahead of time. But 13 minus minus 19, nope. This one's not quite as obvious to me, but I can do this. 13 tenths, okay, minus 6 tenths. There we go. Nope. Minus more than that. 13, negative 20, 34? I apologize, I'm not doing very well with this. I'm going to pause and figure this out. Nope, that's the wimpy way to do it, to pause. I'm going to figure it out. Negative 19 tenths plus 13 tenths n minus 13 tenths. So negative 19 plus negative 13 would be my y-intercept. That would be negative 32 minus 32 tenths. So that would be an alternate way of, I don't know why I erased that. I shouldn't erase that. This is an alternate way to write it. Sometimes it's really easy to look and see what the y-intercept was. It wasn't as easy in this case. Now, number 4 is to find the 200th term in the sequence. So a sub 200 is equal to 13 tenths times 200 minus 32 tenths, or I can say a sub 200 is equal to negative 19 tenths, my first term, plus 199 times 13 tenths. So notice in the second form, the more linear type of a format, we're actually plugging in the term number for n in the function. In the traditional way of doing it, this one right here, the explicit rule, we're starting with the first term and then plugging in the term number before it to multiply times 13/10. Either way, though, we're going to get the same answer, which happens to be 256.8 or 202,568 tenths or 1,284 fifths. So any of those answers would be correct. That ends this video. The next video will be geometric sequences.